Sharpen pencils, clear your desk.
It's time to increase your nerdiness with Derek.
That's right, folks. I am your wonderful, extra geeky host, Derek W. Truesdale. It's time to increase your nerdiness. Now, we have some hardcore geeky stuff coming up today. I mean, like, the kind of conversations, if you could get this stuff, and it's not really that hard, we're going to explain in depth the process of sampling, and then another big, huge, awesome vocabulary word. Non-nerds, run away while you have the chance. Quantization. Oh yeah, that's how nerdy we are today. We're going to be talking about sampling and quantization. Now, it took so long to get up the podcast from last week. I don't have viewer feedback, so I guess we'll get right into it. Shall we? Anyhow, I've got some images and stuff here, because the thing about sampling, and as far as the computer is concerned, it's like the first step to get your data into it. There's a transducer in the microphone, which is transformed into electrical impulses. There's a sensor on that camera right there that somehow changes that into electricity. Isn't that weird? How does it do that? Somehow it does, but then the computer has to get its hands on it. It has to be able to quantify this stuff. How do I turn this into a definite value? Now, with audio sampling, I'm sure a lot of us are at least vaguely familiar with a waveform. Looks like this. And you can see it bounces up and down like that. Well, in fact, if you zoom in enough on one of these waveforms, you can actually see the individual samples. And you see those little dots there? Those are samples of this audio waveform. Now, let's talk about the sound first for a moment. We have, here's a theory. There's human hearing, where we can hear way down low, much lower than my dorky voice. But, maybe about 10, 20 hertz. Way down there, a nice low rumbly noise. Like when you go to a George Lucas movie. And then there's the upper range of human hearing that teenagers these days use for a ringtone. You get to about 16 kilohertz, and the old people who are 28 like me have a little bit of a tougher time hearing it. And then by the time it gets to about 20 kilohertz, that's kilo being times 1,000, then it's pretty darn hard for any human to make out what it is. All right, now are you ready for a nice theory lesson? There's a guy called Nyquist, and he was a smart feller who came out with Nyquist's theory, or theorem? I guess when they prove it, it's a theorem. Somebody leave a comment if you're smarter than me on that. And what he figured out is that, let's say humans have the ability to hear up to 20 kilohertz or so. Well, to accurately express that 20 kilohertz, the whole range from the low, low, low to the high, 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 we actually need twice the amount of detail. Now, this is the theory behind CDs, those compacted discs. They're actually sampled at about twice that, at 44.1 kilohertz. Why, golly gee, that's the double of 22,050 hertz. It's almost twice as much. That Nyquist was a smart feller. So that's what we have to do in audio to get this stuff sampled. Now, video is a little bit different. We have these things called pixels. And now get real close to your screen. If you're watching in high def, not where I am, go look at a different part. Don't look at my nose hairs. I know what you're doing, but get really close and you'll see these pixels on the screen. Well, those are the smallest possible dots on the screen. Now, here's the thing. Let's imagine, you remember the Atari 2600? How the Pong ball was a giant block? Imagine a screen made up of blocks, okay? And you want to make a square. Well, that works out nicely. It goes up and over and down and back to the beginning. It makes a wonderful square. You can do it all day on your Atari 2600. Maybe they had a paint program or a video game like Mario Paint. That would be cool. Well, here's the problem with sampling. In the real world, if I was to do a Fruit Ninja style swoosh like this, whoosh, and make a diagonal line, how does the computer quantify that? Imagine that. You'd have a diagonal line going across, and it would have to do this sort of stair-stepping thing. Now, following Nyquist's theorem, we would have to have twice the amount of detail that we can perceive, which is why they're now coming out with monitors with crazy resolution. 4K! That's 4096! Crazy stuff. Well, that's what has to be done. Now, there's a unique thing in video processing that you're actually watching right now. And that is, we have something called color subsampling. Now, here's the thing about, it's sort of a combination of what the brain perceives and how the eye is built. You know how we have these rods and cones in our eyes? Well, now you know. One of them, I can't even remember which is which, but one of them perceives color, and one of them perceives brightness. Guess which one, let's do a quiz for you folks in the chat. Which one do we see better, color or brightness? Any answers yet? It's trivia time. I'll give you 5 seconds to answer. 4, 3, brightness! There you go. I'm glad you folks answered it correctly. Now, we perceive brightness way better than we perceive color. Now, the guys who designed television took advantage of this fact, and they actually subsample color. They don't take it in as high resolutions. Now, there are a bunch of fancy ways of doing this, and I'll just show them in brief with, what is it? A 4x4 block. All right, I've got some 4x4 blocks. You see them right there? And digital video is here on the left, and it actually samples color of 4 blocks at a time, right across like that, which is kind of crazy when you think about it. Now, those of you watching on YouTube and the internet and all that, you actually are seeing the one on the right. It's called YV12 or 420. And what that means is it samples a 4x4 block at a time. You watch a DVD or Blu-ray, that's how they do the color sampling. Now, how hard is it to tell the difference? Now, if it's a photographic image of a human being, it's kind of hard to tell. You'd be surprised how much it can trick you. I actually did an example, and this is where you notice it the most. And that's with screen capture stuff, with colored text especially. So I've got some text. I'm not sure how well you folks on the live stream can see this, but there's colored text on a white background and black text on a white background. And now it's impossible, impossible? Yes, it's impossible to show you the difference at that amount of detail because you're watching it in subsampled color. The only way for me to show it is to zoom in. So thankfully, I have a way of doing that. Now, in RGB computer color, your text would just look like this. All right, so that's the before. Let's find out what happens when we change this to DVD color. Ugh! It gets kind of weird. You could sort of tell that it's blue, but it's a little bit off. Now, those of you with sharper vision, look really close. If you look carefully, you can actually see the subsampling. Well, I'm going to zoom in more because you've got to look even more carefully. All right, so there's the letter X on the right. You can see it in blue. I'm going to bring out my pen for those of you watching on the live stream. If you look on the left very carefully, you can see that right there, there's actually a 4x4 block. All right, and right on the top, if you look really close, you can see just a tinge of color. Just a little bit where it's not supposed to be. And so it is kind of neat how much you don't always notice the sort of spill of extra color there. You really have to look close because we don't perceive color as well as we do brightness. So that's why we have a wonderful thing called color subsampling. Now, we've learned that for moving video, it's harder to tell that. But the time you notice it is when you have very detailed colored text generated by your computer, which is why if you're looking at the chat room and you see all different colored text, it's an RGB color. It's the full resolution. All right, now I'm going to get extra nerdy. So those of you who aren't super, super dorky, just kind of la, plug your ears for a second. And we'll sort of bring it around for a conclusion in a couple minutes here. All right, well, in computers, we have color that's represented by R, G, and B. Now, you've probably seen this as you can type in a hexadecimal value of color. Let's say you had all black. 0, 0 would be the first two, which means there's no red. And then another 0, 0 would mean there's no blue. Or no green, and then another 0, 0 means there's no blue. If you wanted to have solid blue, then it would be 0, 0, 0, 0, F, F, the highest number. That's what we would see. Now, here's what we have. In TV color land, that is subsampled, unlike RGB, we have what's called YUV. Why is that? You got me. But there's YUV, and for some odd reason, the Y is the brightness. That's the thing that's sampled all the way, full resolution. So the black and white part of it is sampled full blast. And this is where originally black and white TV, that's how it was broadcast. Now, when we went to color television, we added the U and the V, which some folks would say, well, it should actually be notated as YCBCR or YPBPR. All right, whatever, dude. But what the PB and PR is, you have the Y, okay, which is sort of your brightness. And then you have these color guys. And that sort of says the difference between the brightness and the color. It's getting a little weird. All right, so the brightness part is called luma. Sorry about that. Brightness. Like illumination, get it? And then the color part is called chroma. Now, if you've actually plugged in component cable onto your DVD player, you've used this YPBPR. The Y is actually green. For some reason, that's how the green is figured out. Now there's PB. All right, so if you go all the way with the maximum positive amount of PB, blue, it would be blue. If you go all the way down, it's yellow, the opposite of blue. Then there's PR, which is red on top, and on the bottom is that green? I don't know. I should have looked this up ahead of time. We'll probably edit that in post. We'll figure it out. Anyhow, that's how the TV color works. So, in RGB computer land, it's full blast, fully sampled stuff. In TV color land, there are a whole bunch of different ways of subsampling. So you kind of have this luma black and white part, and then you've got these two fluctuating color things. And every time you watch a DVD, you're kind of watching all that stuff play out. Just kind of weird. All right, so now for my final thought. What have we learned today? Let's talk about some of the problems with color subsampling. One of them is banding. See, here's the thing about our brain. We're actually not that good at perceiving color, but here's what we can do. We might not necessarily be able to tell very small changes in color, but our brain, like this, will find the line. It finds edges between things. So it's sort of like if you've ever done a contour map in earth science, sometimes on movies like Finding Nemo, there will be this blue sea and then just a slight gradient between, like, let's say there's a dark spot in the middle and it goes very lightly to light blue. Well, our brain will see these weird looking lines going around that is sort of the border between one color and another. Our brains are pattern finders, and that's called banding. So that's one of the problems, not necessarily because of compression, but because of subsampling. And the other place we'll notice this is with radically different edges. Like I said, our brain notices edges like that. So here's a great example. If you've ever taken your digital video camera outside and you've had like the sun shining behind someone, and then there's like a person that's much darker than the super, super white background. Well, if you look at those edges, it's like, ugh, it just looks horrible. And one of the reasons is because of the color subsampling there. So there you have it, folks. Much more interesting stuff to come in the future. Let's take a break now that we've learned what quantization is, and color subsampling, and why PBPR. Hopefully you've learned at least one or two things, even if you were kind of half paying attention. And that's it for this week's edition of Increase Your Nerdiness, the podcast that you can find at DerekForPresident.com. See you next time.
Sharpen pencils, clear your desk.
It's time to increase your nerdiness with Derek.